Okay, so we've done ceramics. The next material that we're going to think about is something called a polymer. All right, and before we start doing this, let's just think about the word polymer. So if you look at the first half of this word, we've got this thing here called poly. Okay, and poly comes from the Greek meaning many. All right, so that's from the Greek word for many. All right, now what I've got here is ethene. Now ethene is not a polymer. All right, but we're going to think about polymers by using the example of ethene. All right, so ethene, the formula is C2H4, which means that there are 2 carbon atoms and 4 hydrogen atoms. Okay. Now let's imagine that this here is a molecule of ethene. Now, ethene doesn't actually look like this. I'm just drawing it like this because it's simple. But remember, if I was to blow this up, actually I'm going to have 2 carbon atoms and 4 hydrogen atoms. 2 carbons, 4 hydrogens. Now we haven't talked too much about this kind of thing before, but don't worry about it too much. Just remember that if it's C2, it means I must have 2 carbon atoms, and if it's H4, it means I must have 1, 2, 3, 4 hydrogen atoms. But that's what a molecule of ethene looks like. So when I draw this circle, I don't want you to start thinking that it looks like a circle. It doesn't. Okay, that's just a representation. It's just a model for something else. Okay, now let's imagine that I've got lots of molecules of ethene. Okay, I can join them all together in a chain like this that goes on and on and on. All right, so you see here I have individual molecules of ethene, individual molecules. But here I've joined many individual molecules together into a chain. And that gives me polyethene or polythene. Okay, now polythene, you all know. Okay, polythene bags. Okay, it's a very, very commonly used plastic. Now polythene is many ethene molecules joined together. So all of these ethene molecules have been joined together to make polythene. And all of these bonds, so all of these forces between the ethene molecules, they're all really strong. Okay, so we end up with something that's really strong, all right, and it's really difficult to break down. So I want you to think now about a plastic bag, okay, which is made of polythene. Now you might be thinking that plastic bags aren't that strong and that you can, if you grab a plastic bag, you can pull it apart, all right? But if you think about it, that plastic bag is really, really thin, all right? It's sometimes you can see through those plastic bags, okay? So if you had a big piece of polythene, like a big piece of wood, it's actually really, really strong, which is great, because you can put all your shopping in them, and even though it's really light and really thin, it can still carry all your shopping. The problem is because it's difficult to break down, okay, it means it's bad for nature. So you'll notice when you go out for a walk, you might see plastic bags in the bushes. They can't be broken down by nature. That takes a really, really long time for nature. Because these bonds are so strong, it takes a really long time for nature to be able to break them down. Okay, so that's not so good. All right. Now, this polythene, this is an example of a synthetic polymer. Okay. What that means is the word synthetic means, okay, not natural. Not natural. Has to be made. Okay, so polythene doesn't really, plastic bags don't grow on trees, I guess you could say. There's no polythene naturally occurring. We take ethene and we make it into polythene. All right. However, there are natural polymers. And you have already met a few of these natural polymers. One example would be carbohydrates. Okay, so if you remember, what do we use carbohydrates for in the body? Energy. Okay, now, when the carbohydrate goes into the body, eventually it's going to end up in the mitochondria of the cell in order to be used to release energy. So if we have a look at that, hold on. So I've just turned back in my book to where we did about the digestive system and the respiratory system, getting us things we need for respiration into the mitochondria. You'll remember that carbohydrates, we eat carbohydrates, and then that eventually comes down into the bloodstream and we use it in respiration. But there's this critical process here where carbohydrates get broken down into glucose. And that's the important thing, is that carbohydrates get broken down into glucose. So if we go back to here, all right, carbohydrates are actually long chains of sugar molecules. Long chains of sugar molecules. All right, so we can have, imagine you've got glucose, 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 glucose. All right, and then you'll remember that carbohydrates, the enzyme, can come in and it will break all of these links between the glucose molecules, and then the glucose molecules can then go on to be used in respiration. Okay, so a carbohydrate is a polymer of lots of glucose molecules. All right, so can you think of another natural polymer in the human body? Hopefully you're thinking of proteins. Okay, and proteins are long chains of amino acids. And it's the same thing with the amino acids. Protease, the enzyme, comes in and breaks down the proteins into individual amino acids, which can then be absorbed into the body. Okay, so we've got two types of polymer. We've got our synthetic polymers that we make, okay, typically plastics, and we've got natural polymers that occur in nature and in the human body, like carbohydrates and proteins. Okay.